Okay, so now we want to look at some examples of applying the concept of impulse to solving a couple of problems. The main concept with these sorts of questions is that if we know the initial and the final momentum, then we know the change in momentum, which is the impulse. The impulse is then equal to the force times time. That means if we can find the amount of time that the force is applied, then we can find the average force. Or, I suppose, if we have the average force, then we can find the time. Alright, so our first example has to do with crash testing a car. We have a car and an 80 kilogram dummy that drives into a wall at 25 meters per second. And we want to estimate the average force that the seatbelt exerts on the dummy upon this impact. We want to assume that the car moves 1 meter after impact as a result of its crumple zone. So we want to find the average force acting on the dummy. To figure that out, we need to figure out two things: the change in momentum of the dummy and the time that it takes for the dummy to come to a stop. I guess I should mention here that if we give you a velocity in meters per second, it is a useful trick to convert the velocity into miles per hour, because your intuition about miles per hour is probably much better than it is for meters per second. In any case, the trick is that you double the speed in meters per second, and then you add 10%. So you double 25 meters per second and get 50. Then you add 5 to 50, since 5 is 10% of 50, to get a speed of 55 miles per hour. That means that the velocity of the car and the dummy is about 55 miles per hour. So it is a reasonable value for a car, but we are talking about a collision at a pretty high speed here. Alright, let's find the change in momentum first. So the change in momentum is equal to the impulse, and that is equal to the mass times the change in velocity. We just need to know the absolute value of the change in momentum, so we're going to multiply the mass, 80 kilograms, times the change in velocity, which is 25 meters per second, since we're going from 25 meters per second to 0 meters per second. And that gives us a change in momentum of 2,000 newtons per times seconds, or 2,000 kilograms meters per second. Next we need to find the time. So this is a little trickier. We know the distance that the force exerts is 1 meter. We also know that the velocity goes from 25 meters per second to 0 meters per second. So the average velocity is 12.5 meters per second during the collision. So the average velocity times time is equal to the distance, so the distance divided by the average velocity is equal to the time. That means that if we take 1 meter and divide it by the average velocity of 12.5 meters per second, then that gives us a time of 0.08 seconds. Okay, so now we have the change in the momentum and the time of the collision, so we can solve for the average force. The impulse, or change in momentum, is equal to the force times time, so the force is equal to the change in momentum divided by the time. If we do this, we find that 2,000 kilograms meters per second divided by 0.08 seconds gives us an average force of 25,000 newtons. We're also asked by how much of an acceleration the dummy experiences. So here we have the force and the mass, so we can just divide the force by the mass to get acceleration. If we do this, we get 25,000 newtons divided by 80 kilograms, and we get 310 meters per second squared. So this corresponds to what, about 30 G's of acceleration? So yeah, a collision at 55 miles per hour or 25 meters per second is pretty nasty. It's worth mentioning that the stopping distance here is inversely proportional to the force and the acceleration. If you can double the stopping distance, you can cut the acceleration and the force in half. That is why crumple zones are so important to the safety of vehicles and crashes, and the larger the area that a car can compact, the safer the vehicle is. So that means that the momentum change that the people in the car experience gets significantly smaller the larger the area that that car can compact. Alright, so we've got a second problem here, one that you guys are going to do in the classwork next. So here we have a 1,200 kilogram car traveling at 28 meters per second, and then it quickly stops in 4 seconds to avoid an obstacle. Ultimately, we want to find the average force that the car experiences and the acceleration that it experiences, but I've scaffolded the problem and broken it into into a couple steps here. Our first question in the scaffold is, what is the initial momentum of the car? So the momentum is equal to the mass times velocity, so this guy is pretty straightforward. We multiply the mass, 1,200 kilograms, by the initial velocity, 28 meters per second, and we get the initial momentum, 33,600 kilograms meters per second. The second question in the scaffold is, what is the magnitude of the impulse needed to stop the car? We start with the initial momentum that we just found, 33,600 kilograms meters per second, and we want the velocity to go to 0 where the car is completely stopped. That means we would like the momentum to go to 0, so that means the impulse needed to stop it is really just the 33,600 kilograms meters per second. The third part is, what is the average force that stops the car? Now we found in the impulse that we need to, in the previous question, and the impulse is the force times time. So we are given that it takes 4 seconds for the car to come to a stop, so we can divide impulse by time to get the average force. We do that and divide 33,600 kilograms meters per second by 1,200 kilograms, and we get our average force of 8,400 newtons. Lastly, we want to find the acceleration that the car experiences. Well, we have the average force and the mass, so by using force is equal to mass times acceleration, we can divide the force by the mass to get the acceleration. So that is 8,400 newtons divided by 1,200 kilograms, and that gives us an acceleration of 7 meters per second squared. All right, so it's your turn now. So your version of the problem also has some questions about kinetic energy, but you can just use your formula for kinetic energy, where the kinetic energy is momentum squared divided by 2m. That shouldn't give you any extra trouble here. All right, so after this, we have one more video introducing the conservation of momentum.